Hello, everyone. Welcome back. This is Kenan, your MC of this session. In the last session, we had two distinguished laureates sharing with us on their research and inspiring ideas here. Now, it's the time for young scientists and your turn to share your research with us. So we are very glad that we are going to have over 20 young scientists giving us a flash presentation in this breakout room. We will invite the presenters to come out one by one, and as mentioned, each of you will be given 3 minutes. And kindly end your presentation when time's up. We have a timer over here, okay? So everyone pay attention. We have a timer over here, so for your easy reference. And when time's up, you probably need to round up in 1 sentence or just a few words, okay? So if all is fine, without further ado, let's welcome our first presenter, Kyle McGregor. Kyle, please. Thank you.
Cool. Yeah. Hi, everyone. My name is Kyle McGregor. I'm a master's student at McGill University, which is in Montreal, Canada. So I had to come a long way to come here. I study fast radio bursts, which are these brilliantly bright bursts of radio waves that are detected from other galaxies cosmologically. These bursts last for about a millisecond in time, but in that time, they can release as much energy as the sun does in several days. These are incredibly high energy events. I study these bursts using a radio telescope out in Western Canada called the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. It's on the screen right here. CHIME is great because it's very sensitive and it has a very large field of view, about 200 square degrees on the sky, and it can scan the entire northern sky each day as it passes overhead. It detects about 1 or 2 bursts per day on average and has been observing for the past 5 years is about to produce a data release of several thousand fast radio bursts. I'm specifically interested, as this is an astrophysical survey, in quantifying the detection efficiency of CHIME as an instrument to different types of fast radio bursts. Like I said, as an astrophysical survey, CHIME only detects a subset of what's actually out there in the universe. And the mapping from what CHIME actually detects in its observed population to what intrinsically exists in the universe can be referred to as the survey's selection function. My work is interested in probing this selection function through injecting synthetic FRB signals into CHIME's live data and seeing our recovery fraction to different types of bursts. This allows us to construct a statistical model across different types of fast radio bursts of different energies and morphologies, and correct the catalog that we are about to release to give the intrinsic population of fast radio bursts in the universe, which is of interest because there's currently no well-accepted physical model for what causes fast radio bursts. So understanding the intrinsic populations of them is very important for understanding what actually causes these events. So thank you.
Thank you, Kyle. You made a very good time. So next, we will invite Mason. Mason, please.
Hi everyone, I'm Mason. I'm a postdoc at McGill as well with Kyle. And like Kyle and my group mate, I'll be talking about FRBs. But what are they really? So number 1, just remember the 4 Bs of FRBs. They're brief, so lasting tens of nanoseconds to milliseconds. They're bright. They're broadband, meaning that they are seen across a large range of frequencies. And also they come from beyond the Milky Way. So what do we discover them with? Number 2, Kyle just talked about the CHIME telescope. And one of it has a unique telescope design in which it allows for a large instantaneous field of view of about 200 square degrees. And also, it scans across the entire northern sky daily, meaning that it's a very efficient discoverer of these cosmic flashes in the sky, which is exactly what FRBs are. And it's so prolific that we've discovered about 4,000 or 5,000 at this point. There's some nuance there, but I'll spare the details. But also, it's so prolific that it's also it's about tens of times much more. We've seen about 10 times more FRBs compared to all of the other radio telescopes combined. And so what how do we probe them exactly? So number 3, with polarization, which is essentially just the orientation of the electric field. And in number 4, I'm interested in a quantity called the rotation measure, which is proportional to the magnetic field strength and the electron density along the line of sight. And how exactly can we do that? Use that to understand FRBs? Well, younger spiral galaxies tend to be have higher RMs compared to the older elliptical galaxies. And so then number 5, we then measure the RMs for about over 1,000 FRBs. And the idea is that, so the measured values are in blue, the distribution. And if you can see the lines on the right, reductively, the distribution is better fit with a Lorentzian compared to a Gaussian. So a Gaussian is what you expect based on the random distribution of magnetized regions in space. And the fact that we don't get a Gaussian from expectations from the central limit theorem means that we probably see a preferential we preferentially see FRBs from younger spiral galaxies. And so that means the environments are likely younger stellar environments, which could be the case for young magnetized neutron stars, such as magnetars, which is the subject of the 2021 Short Prize in Astronomy. If you want more details, feel free to talk to me, or I'll have a poster tomorrow as well. Thank you.
Thank you, Mason. So next we'll have Kohei Yamada. Go here, please.
Hi, I'm Kyohei Yamada. I'm a postdoc at Princeton University, and currently I work on the Simons Observatory experiment. Simons Observatory is a cosmic microwave polarization measurement experiment. And this Simons Observatory is the largest cosmic microwave background experiment in history. And our project started in 2016, and we finally started observation from last year. And our observatory is located at the Atacama Desert in northern Chile at the altitude of 5,200 meters to reduce the effect from atmosphere. And our observatory is currently consists of 4 telescopes, so maybe you can see the 3 smaller telescopes surrounded by the screen, and also you can see the smaller white telescopes, that's the large aperture telescope. And I'm mainly working for these smaller telescope, and these telescopes are focusing on measurement of degree scale polarization of cosmic microwave backgrounds to search for the primordial gravitational wave. And previously, I also worked on the ultralight axion-like particle searches using the precise measurement of temporal oscillation of Crab Nebula. And we were able to place one of the tightest constraints on ultralight axion and photon coupling constant as shown in the right figure. That's all from me. Thank you.
Thank you, Kohei. Thank you very much. So next we'll have Mike Lau. Mike, please.
So could you advance the slides and play the movie? Yeah, thank you. Hi, I'm Mike Lau. I'm an astrophysicist, and I'll tell you about why and how a star might eat another star or a planet. So if you look up into the night sky, roughly half of those stars are not actually single objects, but binary stars or even more. As you go into even more massive stars, there are triple stars and quadruple stars and so on. And I think the Hong Kong Laureate Forum is obviously a fan of triple stars. As you can see from their logo here, that's a triple star. And the fact that stars are in multiple systems, that completely alters their evolutionary fates and their lives. For example, a star towards the end of its life would expand as a red giant star when it exhausts its hydrogen fuel by up to hundreds of the times of the size of the sun. And so it could engulf and swallow its nearby companion. It could be a sun-like star, or it could be a dead star, like a neutron star or a black hole. This is a phase called common envelope evolution. Is it possible to play the movie again? Thanks. So this is called common envelope evolution, and we think it is a crucial phase in forming many astrophysical objects that we're interested in. So that's the red supergiant star eating a much smaller star, and the smaller star goes in and actually expels most of the fluffy, low-density material that makes up the giant star. We think this is important for forming gravitational wave sources, X-ray binaries, certain types of supernovae, and more. Now you might ask me, is this important for single stars then? Well, even in single stars, many of these have planets, have close-by planets. And we believe about 10% of these stars, when they also grow into red giants, could engulf their nearby planets. And that's another topic that I've simulated or researched into. That's area of planetary engulfment. Is it possible to play the second movie? Thanks. So what we're looking at is a Jupiter-like planet. What happens when it's swallowed by its host star? It's swimming in this pool of stellar plasma. And from its perspective, it's like having a blow dryer aimed at it, and you're blowing off material from that. And we believe all this material could pollute the star. It would give rise to chemical peculiarities that could be observed at the surface. And it could also cause the star to rotate faster, much faster than we would expect them to if there were only single stars. And for both of these topics, I make use of 3D hydrodynamical simulations to study them self-consistently. Thank you.
Thank you very much, Mike. So next, we are going to have Hugo White learn Mac. Hugo, please.
Okay, good afternoon, everyone. So this is Hugo White-Mac, affiliated with CHK and HKUST. So yeah, environmental retrieval and assessment is extremely important to us because it seriously affects our health. So that's why scientists use a lot of approaches in order to do the environmental retrieval task. For example, they use satellite informatics, which is remote sensing. So remote sensing means they have a detector or a sensor installed on board of a satellite such that you can monitor the environmental retrieval or environmental quantities over the entire troposphere, stratosphere, so on and so forth. And then after that, they use the profiles, averaging kernels, so on and so forth, to retrieve what is happening on the ground. So it is an interdisciplinary subject that combines data analysis, mathematics, chemistry, or even atmospheric physics. So I would like to introduce you the satellite informatics, which is based on the forward model assumption. So nowadays, we have satellite mission in different continents as well as different nations. For example, Tempo for US, Sentinel-4, and also Sentinel-4 in Europe, and GEMS, which is a geostationary satellite, which is for the East Asia domain, which gives the hourly resolution profiles and also the atmospheric quantities. Okay, so that's why you see in the figures on the right, so based on a lot of profiles, we can obtain the atmospheric pollutants in the entire troposphere, and then by using inverse method, we can do whatever in ground. Okay, so this is for satellite informatics. Now, and then numerical models have also been developed and also combine different quantities like the land use attributes, and then the meteorology attributes, emission, and then also the gridded data, so on and so forth. And then we have the WRF-CMAC model, which solves the efficient diffusion equation. So WRF is weather research forecasting model, and then CMAC is a chemistry model. So this is to solve the PDE in a numerical manner. And after solving it via modeling approaches, we try to combine the data obtained from satellite informatics as well as from numerical models, and then to fine-tune the algorithms so that we can use the modern data analytic approach like machine learning as well as artificial intelligence, data assimilation, those techniques in order to obtain fine-scale pollutant attributes in our daily lives. So that's something related to my research. Thank you very much.
Thank you, Hugo. So next, let's invite our next scientist, young scientist Bingxiao Liu. Bingxiao, please.
Hello, everyone. My name is Bingxiao Liu. I'm currently a postdoc at the University of Cologne, working on differential geometry. Today, I would like to introduce one of my research topics since my PhD thesis, which is the theory of hyperelliptic Okay, it doesn't work. Hyperelliptic Laplacian developed by Jean-Michel Bismuth. Over 20 years ago, Bismuth initiated this program to understand in a geometric and explicit way the connection between the spectrum of a Laplace operator and the geodetic flow on a given Riemannian manifold. This could provide a new approach to the Fried conjecture in dynamic systems. The main idea is try to construct a smooth family of hyperelliptic differential operator, which on a bigger space called the cotangent space of M, which interpolate between two fundamental elements. One is the elliptic Laplacian on the original manifold. Another one is the generator of the geodetic flow on the cotangent space viewed as a first-order differential operator. So the key point, also the very challenging part in this theory, is to identify the spectral quantity which remains meaningful and also preserved under this deformation or this interpolation. This way, you can connect one side to another side with this parameter B I put there. And the one striking and also successful example from this idea is Bismuth's formula for the semi-simple orbital integrals. Here is the formula. It looks simpler, but every term is more complicated. Then, unlike the traditional representation theoretical method by Harishchandra, Bismuth's approach is more geometry. It makes it more practical when we use this to study the geometry of locally symmetric spaces. So in my thesis, I extend Bismuth's formula to the case of a twisted orbital integral and the twisted trace formula. And use this result, I also study the asymptotic of rectangle analytic torsion for the locally symmetric spaces. And also I want to mention the work of Shu Shen, who gives the complete solution for the Fried conjecture using this formula. Okay, that's all. Thank you.
Thank you very much, Bing Xiao. Next, we will have Jiepeng Fang. Jiepeng, please. Jiepeng, please.
Hello, everyone. I'm Jiepeng Fang, a postdoc in the Department of Mathematics in HKU. Today, I will talk about the positivity properties of canonical basis based on a joint work with Professor Xu Huahe. The quantum group was introduced by Jinfield and Jimbo around 40 years ago. It is a very important mathematical object related to many branches of mathematics and mathematical physics, such as Lie theory, representation theory of qubits, topological invariant theory of knot theory, statistical mechanics, conformal field theory, and so on. And Lucid introduced the canonical basis in 1990s. He proved that this basis has very remarkable positivity properties. The canonical basis of the positive part or the negative part of the quantum group has the positivity with respect to the multiplication and the co-multiplication. That is, the structure constant of the canonical basis with respect to the multiplication and the co-multiplications are Laurent polynomials with coefficients in non-negative integer. And the canonical basis of the negative part naturally gives the canonical basis of the simple high-3 module. And he also proved that the canonical basis of the simple high-3 module also has the positivity with respect to the action by several generators. And it is natural to consider the tensor product. And Lucid and later Bao and Wang introduced the canonical basis of the tensor product of several simple low-3 modules with simple high-3 modules. In general, the canonical basis of the tensor product is not the same as the tensor product of the canonical basis. And it is natural to consider the question whether the canonical basis of the tensor product have the positivity. And in my joint work with Professor Xu Huahe, we proved that the canonical basis of the tensor product indeed has the positivity. We proved that the transition matrix from the canonical basis of the tensor product to the tensor product of the canonical basis have the positivity. And also, these bases have the positivity with respect to the action by the canonical basis of the positive part and the negative part. Our approach is inspired of the geometry theory of total positivity. We introduce the thickening conjunctions, which enable us to embed the tensor product into a negative part of a larger quantum group. And then by the positivity of the canonical basis of the bigger quantum group, we obtain the desert positivity of the tensor product. Thank you very much.
Thank you, Jie Peng. Then we will have Leaf Lei. Leaf, please.
Good afternoon, everyone. I'm Leaf. I'm based at the KIAA and BIMSA in Beijing. I am what some may call a black hole environmentalist. And what I do is I model and, in some sense, promote the modeling of environmental effects for future space missions, such as LISA, Tianqin, and Taiji. The system that I'm primarily interested are these extreme mass ratio in spirals, or EMRI for short. These systems consist of a supermassive black hole bound to a small orbiter, typically of solar masses, forming a binary of 10 to the 4 to 10 to the 6 solar masses. In my most recent work, I studied a phenomena called quasi-periodic eruptions, and these are quasi-periodic X-ray bursts, and one way that we can model them is with an EMRI with disk collisions. When the orbiter collides with a disk, it produces some electromagnetic radiation in the form of a shock. And this shock changes the orbital morphology of the EMRI. And what happens is that we can see the change in the gravitational wave signals over long timescales. In the middle panel, the blue is the EMRI waveform without the disk, and the red is the EMRI waveform with the disk. And as you can see, at early timescales on top, they are completely in phase. And as time progresses, you can see that they slowly grow out of phase. And if you plot this on a frequency spectra, as seen in the very last panel on your right, you can see that they have a significant deviation in the waveforms. And for less eccentric waveforms as seen on top, they do not pierce the noise curve of Tianqin and LISA. But in the bottom, we can see that they start to pierce the noise curve because the higher harmonics enter the detectability band. More recently, I've been thinking about other aerodynamical effects, such as Magnus forces and spin-induced aerodynamical effects. And I'm going to talk about this in my poster presentation. So I hope you can come to that. And if you would like to look at the paper, please scan the QR code on the top right-hand corner. Thank you so much.
Thank you, Leaf. Please be seated. Then we will have Davun Kim. Davun, please.
Okay, hello everyone. My name is Taewon Kim from National Institute for Astrophysics in Italy. Today I'd like to introduce one of the setup or the method in X-ray astronomy for studying the extreme physics around the black hole, which call it the X-ray polarimetry. The polarimetry, is the fascinating tool for studying an additional dimension of the light beyond the polarimetry, imaging, and the spectroscopy. And however, this new polarimetry in high energy band, such as the X-ray, has been limited to the technological challenge. But however, this amazing X-ray polarimetry explorer, breaking thanks to the detector technology developments, we now have this XP, Imaging X-ray Polarimetry Explorer, which is the first mission between the NASA and Italian Space Agency for studying X-ray polarimetry from the window. So taking advantage of this XP, we can firstly study the X-ray polarimetry emission from the X-rock elliptic system. So taking these advantages, we are studying the active galactic nuclei, which hosts the supermassive black hole at the center of them. And especially the X-ray emissions from AGN is arising from the relativity jet, innermost region of the relativity jet and corona, and the reflected emission from the accretion disk and dusty torus. what we can do with the polarimetry is the polarization is a key tool to investigating the structure of the magnetic field, and we can constrain the geometrical property, the emission state. So these are figures. I'd like to briefly summarize what we discovered until so far with the XP. So from our XP measurement of the relative jet, we found a high X-ray polarization compared to the longer wavelengths in the optical and radio band. So we found this kind of the energy stratified the structure, and which is suggesting the shock acceleration mechanism from the relative jet. And also, we firstly discovered the helical, actually the polarization angle rotation in the X-ray band, which is suggesting the presence of the helical magnetic field inside the jet. And then for other, I have 10 seconds. So with the corona, we constrain the geometry as a slab and wedge-like the geometry. And our polarization measurement, which is a little bit high and perpendicular to the direction of the jet, suggests there are reflected component surrounding the core and the edge.
Thank you very much, Taun. We look forward to your sharing afterwards. Thank you. Please be seated. And now presenter, and the next one will be Anthony de Saint-Germain. Anthony, please.
Okay, timer started. 3 minutes. There really is a timer. Okay, hello everyone. I'm a mathematician here at the University of Hong Kong. I'm a postdoc with Professor Xu Huahe, the same lab as Jie Peng. But today I want to, actually, you see I have no posters, so you have to look at me. So I want to talk about something which is slightly different. I'm not going to talk about my research area. What I want to talk about is the digitalization of mathematics, right? And in order to sort of make sense of that, let me just sort of point out that so digitalization is something that has appeared ever since the appearance of the digital computer, right? And ever since the appearance of the digital computer, so many industries, professions, even hobbies, been completely transformed, right? I'm not making comments about good or bad, but completely transformed by the digital computer, right? You can think of the music industry, probably 50, 60 years ago, you had to play an instrument to be able to be a musician. Now, it's not so sure, right? So digitalizing sectors and industries has a transformative effect on those sectors. Just yesterday for dinner, I think I was sitting next to a PhD student in the life sciences. He's training to be a doctor. And he was telling me that thanks to the digitalization of data associated to patients, they were able to use machine learning techniques to improve, the diagnosis of certain diseases. Right? In order to make use of these technologies, you need to digitalize whatever it is that you want to be working with, right? You digitalize music first, and then you can do digital music. One area where digitalization is really lacking is academia. Most, at least theoretical researchers, research the same way that they did 50 years ago, maybe modulo using an iPad to write instead of a blackboard, right? So digitalization hasn't really seeped through academia yet. But this is changing. In the last sort of 10 years, at least in pure mathematics, there's been a sort of a big collaborative effort to generate a digital library of mathematics called MathLib. This is only step one, maybe, of like the theoretical sciences. Maybe digitalizing mathematics is easier. And so this is essentially what I wanted to present to you today, but 3 minutes is not enough to say anything meaningful, so all I'm going to do is tease you and say, if you want to know more, you come to see my poster. That'll be tomorrow morning. Thank you.
Thank you very much, Anthony. Please be seated. Thank you. And next, we will have a lady, Maria Zedrick. Maria, please.
Hi everybody, I'm Maria, I'm a postdoc at the University of Edinburgh, and I will selfishly talk about my research. So my main focus, I'm particularly interested in the dark sector of the universe, so all the things we cannot see, the 95% of the universe, namely the dark energy and dark matter. So dark energy is something that tells the universe to expand in the accelerated manner, and dark matter is something unseen, something that basically builds the underlying structure of the universe, the cosmic web. And this cosmic web, this kind of like spider web, is telling the visible matter that we can actually observe where to form galaxies and all the other structures and solar systems, so everything we are made of. My particular interest is also in the exotic dark energy models, so basically all the dark energy models that are not cosmological constant. One model I worked a lot on is called the dark scattering model, which is a subclass of interacting dark energy models, which is basically saying we have dark matter, we have dark energy, we have no idea what it is, so let's assume both of them interact with each other. And let's assume they interact with each other by exchanging momentum. So if we have a particle of dark energy and we have a particle of dark matter and they kind of like scatter, and let's imagine like, well, the dark matter particle is the building block of the universe, and the dark energy will give it an extra boost so that this particle can travel to very large distances, so the largest structures can form on the large scales. On the other hand, what if this dark energy particle will kind of like repress or give like extra friction to the dark matter particle so it not move that far away, so that we have a suppression of the large scale structure on large scales? The same principle also works in the other way, so that on smaller scales, because we have an extra friction, the dark matter particles cannot really escape already collapsed structures, while if you have this extra boost, then the particle kind of like stream away from the collapsed structures and you have a suppression of structure growth. So we know that this model will introduce some changes in our structure formation. Hence, it will also introduce changes in where the galaxies are distributed, not only where they are distributed, but also how the shapes of the galaxies are changed or distorted, because we know that light interacts with matter. So we know that this model will introduce some changes in our structure. What we can do, we can then model the observables that we can observe with our telescopes. And what we do next, well, we have data, we have models that we develop, and we apply the Bayesian inference. So basically, we just explore the multidimensional parameter space and try to find the best parameters that can explain the model and the data. And here you can see the posterior distribution, which is basically telling you that the region in the dark shade gives you the best agreement between the model and the data.
Thank you very much, Maria. Thanks for the sharing. And next, we'd like to invite our next speaker, the presenter, Shuanghe Fang. Okay, Shuanghe is here. Round of applause. Thank you.
Okay. Hello, everyone. My name is Shuanghe Fan from Tsinghua University. The title of the talk is Higher Order Hessian Metric Theory and its Applications in Calabial Manifolds. One of the fundamental problems in algebraic geometry and singularity theory is to investigate whether two given smooth projective manifolds X and Y are projective equivalent. In hypersurface case, when their defining equations have degree 2, this can be resolved using quadratic form theory and classical Hessian matrices. For cases with degrees greater than 2, in this talk, we shall develop the novel higher-order Hessian metric theory as a generalization of classical Hessian metric theory. With this method, we solve a several decades-old problem about the classification of complex structures of K3 surfaces in CP3. Consider the one-parameter family of Calabial manifolds. This is defined by the polynomial of the first power of x1 plus the fourth power of x4 plus t times x1 times x2 times x3 times x4. If this polynomial equals to 0, let this polynomial be 0, and we can get xt. For arbitrary t1 and t2 in the complex field, xt1 is projectively equivalent to xt2 if and only if the first power of t1 is equal to the first power of t2. It is obtained from the higher-order Hessian metric theory. From this theory, I got many projective invariants, and using this projective invariants, I can get this conclusion. Thank you.
Thank you very much, Shankar. Then we will have David Russo. David, please.
Hello, everyone. I'm David Russo. My home institute that pays me is the Deutsches Elektronensynchrotron in Hamburg, Germany. But most of my research is done as a particle physicist as part of the ATLAS collaboration at CERN. But that's not astronomy. So I'm going to instead be presenting this random side project I'm doing with this PI at DAISY on developing new detectors for high-frequency gravitational waves. Now, you might be wondering, why should a particle physicist care about high-frequency gravitational waves? Well, I mean, at least unlike Susie, we know gravitational waves exists, but mainly there's very interesting signatures for new physics that line the higher frequencies. For example, primordial black hole mergers, or what's particularly interesting to us is axion superradiance. So of course, axions are these really cool particles that solve a couple of very important problems in standard model physics, in particle physics, two birds, one stone. And there's a signature where rotating black holes should have an axion field around them that will emit monochromatic gravitational waves. But these will be in the higher frequencies that are beyond the traditional established observation range of LIGO and Virgo and so on and so forth. So we need new detectors to get around this. And this main challenge is because, of course, like you have an interferometer, so the quantum noise becomes actually quite important. And if you have high frequencies, that becomes an issue. So you need new detectors. So most of these new detectors that are being proposed, is kind of like a race at the moment with many different concepts, revolve around resonance. So you try to couple the light to some resonator to increase your sensitivity. So our concept here is that we're coupling the light in the interferometric cavity to a high Q factor, very lossless membrane, which, for example, can look like this or like this based on the frequency design. And basically, this gets you past the shot noise. Interestingly, also, you can tune the resonant frequency of this by just increasing the laser power for projecting 0 to 20 watts. And because you use optical trapping, you basically make the membrane a bit stiffer. I'm speaking way too quickly. I'm sorry. Yeah, so I worked on designing these membranes and trying to make them as lossless as possible, and also simulate it in COMSOL to try to really understand how these things would work in a real detector and what are the loss mechanisms. So, for example, you can see here, for example, even at 10 to the minus 11 torques, we're still gas damping limited. So actually, it's okay if the members are not as lossless as they need to be. And then, of course, you have mechanical damping, which is in yellow, and then photon scattering, which is a bit less than that. But yeah, so interestingly, so we do have competitive sensitivity to other detector concepts. But more interestingly is we can also use this as a detector for vector dark matter, because of course if a vector dark matter field is going through this thing and the material of the membrane is different than the material of the mirror, then of course it's based on Z and A, you'll actually get a differential force between them. So sorry for this very chaotic talk, but that's basically it on my side.
Thank you. Thank you, David. Please be seated. And next, we would like to invite Winky Lee. Okay, Winky is here. Okay, round of applause to invite her. Thank you.
So hi everyone, I'm Winky. I'm a PhD student from the University of Edinburgh. So I work on star formation and quenching of the dwarf galaxy. Before I start, let me give you a bit of the background so you can understand better about my study. So in astronomy, we want to understand how galaxies evolve and how the structure are formed from a large scale. So there has been a lot of research on the massive galaxy, and most of our models and simulation calibrate based on the observation from the massive galaxy. But dwarf galaxies, actually, they are there, and they are actually abundant in the universe. So they actually form an essential part for us to understand the galaxy evolution from a bigger picture. But previously, they are difficult to observe because they are fainter. But now, with a more powerful telescope, we can observe them up to further distance and down to a lower mass. So in terms of star formation activities, galaxy can be classified into two types: star-forming galaxy and the quiescent galaxy. Quiescent galaxy is the galaxy where the star formation has been stopped. So for dwarf galaxy, we find that quiescent galaxies within the mass range of 10 to the 7 and 10 to the 9 solar mass, they are almost always found next to a more massive galaxies. So in other words, it's very rare to find an isolated quiescent dwarf galaxy. So this means it comes to the conclusion that the dwarf galaxy are almost always quenched by the being next to a more massive galaxy. So in our study, 55 galaxies, dwarf galaxies, are selected from the MATLAS dwarf galaxy catalog, and we perform follow-up integral field spectroscopy observation. Firstly, we need to classify this galaxy into star-forming or quiescent galaxy. We can do so by checking whether the spectrum of this galaxy contains emission line. So out of the 55 galaxies we study, we find there are 18 of them showing emission line, which imply underlying star formation activities. And the non-star forming dwarf are always found closer to the massive galaxy on average. And this is consistent with the hypothesis that being next to a more massive galaxy is a necessary condition to quench the dwarf galaxy. And that's one thing we have to point out. So on the figure on the right, so you can see we are comparing.
Appreciate it.
Yes, sorry.
Thank you very much, Winky. Let's hear your sharing more later. Thank you. After Winky's presentation, next we'd like to invite Alice Owen. Okay, Alice is over here. Okay. Alice, please. Thank you.
Yes. Hi, hello everyone. I'm Alice Owen. I'm a postdoc fellow at RIKEN, which is a national research institute in Japan, just on the outskirts of Tokyo. And I'm interested in cosmic rays and what they can do to the evolution and formation of galaxies. So my research takes four general themes: what cosmic rays can do to the internal part of the galaxy, the interstellar medium, how they can change the circulation of gas between a galaxy and its halo around the galaxy, how they can change the formation and development of these outflows, which are a key component of the feedback recipe in galaxy evolution, and what they can do in general to the circumgalactic medium. So ranging from small scale to large scale, cosmic rays can do things like change the thermal and physical conditions of the multi-phase interstellar medium, change how that gas can convert into stars. It can change the development of these outflows and change the way in which the pressure from these cosmic rays can drive these flows, which can be important in modifying how gases are recycled into a galaxy. They can add an extra pressure component to the circumgalactic medium, which can make it harder for gas supplies to reach a galaxy in the early stages of galaxy evolution. And they can also add this pressure component to the circumgalactic medium as well, which can make it harder for these outflows to erupt from a galaxy and reach far into the circumgalactic gas. So if you're interested in this topic, please check out my poster, which I think is already on display, but available tomorrow. And also, if you have lots of time, you can read my review paper as well in the bottom left-hand corner. Thanks a lot for your attention.
Thank you very much, Alice. The following will be Zainab Vayaz. Zainab, please. A big hand to welcome her. Thank you.
Hello everyone, I am Zainab and I am an undergraduate from PolyU, and I have recently done my research in collaboration with Western University in Canada. So my research focuses on pi emission in 6 to 9 micron range specifically. And so PAs are polycyclic aromatic hydrocarbon molecules, which are like large stable molecules made of hydrogen and carbon, and they basically absorb visible light, and then they re-emit it in infrared radiation, which is then detected by the James Webb Space Telescope, as it is an infrared space telescope. And then we study its data, and my particular focus is on from 6 to 9 micron range, particularly 7.7 band and 8.6 micron band. And I use several other well-known bands in comparison to it, which is probably not clear on the screen, but I used bands 6.2 and I used bands 11.0 and 11.2 in order to compare, because we know the behavior of these bands. So 6.2 is a cation band, whereas 11.0 and 11.2 is a neutral bands. So as we see in round 1, where we use these 5 basic bands, we see that 8.6 is the blue arrow and 7.7 is the green arrow. So in all 3 continuums, this is global continuum, this is local continuum, and super local continuum. So the difference between these continuums is that it removes the background dust and other particles that actually hinder with the data that we are trying to get. So the 8.6 and 7.7 micron band are actually more clearer the further continuum subtraction that we do. So we see that 8.6 and 7.7 bands basically align with their patterns with 6.0 band, which means that they behave as cation bands. However, in our round 2, we divide the 11.2 band into 2 further components, which is 11.207 and 11.25 micron. And over here, we see that 11.25 band actually dominates the distribution of all the bands in our biplot, and which suggests that it most likely, instead of being individual PA bands that we could study, it's more likely a PA cluster or some other kind of features that we yet do not know about. And so as 11.25 micron band was dominating our results, we removed 11.25, but we kept 11.207 band for a round 3, and we saw that in this round, 8.6 band, which is the green arrow, basically behaves like 11.0 and 11.207 bands, which are neutral bands. So they change their behavior from cationic to neutral bands. And this shows that 8.6 bands basically behave as transitional, have a transitional nature, whereas 7.7 bands acts like cationic bands. So in order to know more about the results, please visit my poster presentation tomorrow so we can discuss more. Thank you.
Thank you. Good time. Zainab, thank you very much for your sharing. So upcoming, we will have William Vevo. William, please. Another round of applause.
All right. Okay. Welcome, everyone. I'm William. I'm a PhD student at the University of Toronto, and I work at the intersection of analysis and probability. And I will try to explain that somehow, in math, but also in astronomy and medicine, randomness appears, and so in some sense, all of you should care. But I'll talk about my research more, and it's usually motivated by problems that come from physics. And I'll try to explain first these sort of objects that I might look at or that we care about. So first, physicists as a whole would really love to have a random function, something that they could test some models on. But it's quite a lot to ask for, and we usually make simplifications, and we'll ask that this is given by a Gaussian random variable. So think of this bell curve in statistics. And if you're given this, it suffices to know what are its moments and also its variance or covariance. And so in this case, we'll ask that its covariance is given by this thing called the Green's function. So the Green's function appears in a lot of problems in physics and math. It's basically solution to the Laplace equation in differential equations, if you know what that means. But it's related to this heat equation, basically. And so under these two restraints, we've defined this random object, which we take as a model of a random function. The problem that physicists often disregard is that this Green's function has a singularity on the diagonal. There's a blow up. And so the object that I've just described is not well defined. But now there's a big theory of to make sense of it in terms of what we call distributions. And so it's actually well understood. And it's this object that I've written as phi on this slide. Now what's even more intricate to understand is exponential of this object. Again, because this object is not a function, taking exponentials of it is non-trivial, but there's also a big theory to make sense of this rigorously. And this is the theory called multiplicative chaos. And it was actually studied by a mathematician first who was interested in what happens to products of random variables. But now people have used these objects to talk about random geometry and also construct these sort of canonical random surfaces that are basically Riemannian manifolds whose metric tensor is given by random metric of the form that you see on the board there. And again, you need this theory of multiplicative chaos to make sense of these objects. But I think that even the foundations of these things, the way we construct them and the way we define them is not properly set in mathematics, so not rigorously understood. And so part of my work, or part of what I want to do, is to, again, put some of the foundations down behind these work and make sense of the objects that some physicists have been studied, but perhaps without the sort of rigor that we would want to make to give full proofs of some conjectures that are in the area. Thank you.
Appreciate it, William. Thank you very much. And our next presenter will be Mikhail Borikhanov. Mikhail, over to you. Thank you.
Good afternoon, everyone. I am Mikhail Borikhanov from Institute of Mathematics and Mathematical Modeling. Today, I will talk a little bit specific topic, but for that reason, with my colleague Nordolet, we will divide it to steps to manage our time effectively. So here, since there are a lot of, we come from different fields, I will keep the explanation intuitive. And to visualize our solutions, blow up and the global solution, let's look the next examples. First, in a daily life, pumping air into a balloon, at first it expands bigger and bigger, but eventually at some time it bursts suddenly, so it's blow up. In other words, blow up, it's when something grows too fast, becomes like uncontrolled. And next, if you will think about candle burning, it slowly melts away until it's gone, but never explodes. In other words, it continues to exist and change smoothly for all time without blowing up. So I tried to make a connection with another fields, like a medicine, like a cancer cell. In this case, in cancer cell, like a malignant, I think it's a good pronunciation, malignant cells may divide so rapidly that tumor size grows exponentially until the body cannot cope. This is like a blow up. It made with the help of AI. I think it's correct. In other words, it's like an example of a blow up. And when we are talking about global solution of related to medicine, it's a normal wound healing, like cells multiply and repair tissue, but the process is regulated, eventually stabilizing as the wound closes. When we are talking about astronomy, it's a supernova. Supernova is a star after fuel exertion collapses and then explodes in seconds with enormous energy release. It's a classical finite time blow up. And then moreover, related to global solution, we can give an example of our planetary orbits, because Earth orbits the sun steadily for billions of years, a stable global solution that persists indefinitely. In a mathematical side, from the school, we know that when we divide one number, another number, we have like a exact number, but we will divide one number to 0, we have like a blow up. Thank you.
You very much, Mikhail. Let's exchange more ideas after the session. Yes, and next we will have Nerdalat Tobakhanov. Big hands to him. Thank you.
Oh. So good evening, everyone. My name is Nerdalat Tobakhanov, and as you remember, it is a continuation of the previous talk. And what I can say, the interesting part is already past. So it's time to the theoretical part. Okay, let's start from the elementary mathematics. In elementary mathematics, what we have? So we have some equation, and we have a exact solution, or its exact number, or exact group. But when you go to the higher mathematician, like especially in PDE, most of the PDEs doesn't have an exact solution. So the question, what is the solution, will change to the, does the even solution exist for such kind of PDEs? So it was our interesting question. So first, first in 1960, Fujita Hayakawa considered the heat equation. The heat equation is the other one without these two. So for other mathematicians, two plays a crucial role. So instead of biharmonic operator, they consider the harmonic operator, and the heat equation actually smooth and it is nice. But if you add the nonlinear term, to the power of p, everything will change. So depending on the power of p, he gets the following results. So he showed just a number p is if it is less than 1 plus 2 over n, this equation blows up, which means the solution goes to infinity. So we have only local solution, but after some time, the solution will go to infinity. So the right exact time before this blow up appears, we say it's lifespan of solution. So what we do? So we have a Fujita result for the heat equation. So as a mathematician, we love to generalize everything. So our question was, what happens if we just consider instead of Laplace equation, Laplace operator, biharmonic operator, and instead of the whole domain Rn, what happens if you consider in exterior domains? So this question was in our work, in this work, and we have found some relative phenomena, same as the Fujita. And our Fujita critical exponent, as you can see, it is 1 plus 4 over 2. So the biharmonic operator affects on the number 4. So in the Fujita sense, it was just a 2. So overall, it is, for me, it is interesting part of mathematics because we don't know what is the exact solution, but we can still even we don't know solution, we can still have a critical behavior of solutions. So if you are interested, we can discuss more later. Thank you for your attention.
Thank you. Keeping a good time and sharing. That's great. Thank you, Nudalat. Next, we will have Kian Nguyen. Kian, please. Thank you.
Hello, everyone. Thank you for joining me today. So let's begin with something familiar. A protein, we see the intricate molecule at the heart of life itself. It looks impossibly complicated on the left-hand side, but zoom in, you're going to see that it's a precise chain of simple amino acid. Biology unlock life secret by breaking these complex down into simpler one. So my PhD in differential geometry did the same, but not for biology, but for the hidden symmetry that shape our universe. So in geometry and physics, we also have our protein. We call them Killing tensor. The name is very violent, but they are not. They are absolutely useful because they actually describe hidden symmetry, invisible rule that make nature predictable. When a planet orbits a star or when energy is conserved, it's because of the symmetry. They are mathematical DNA of motion, encoding deep order behind what we see. But like protein, they are incredibly complex and very, very difficult to understand. So now let's turn to the slide. So across the bottom, you're going to see some geometric work where I explore this mystery. So we start with the familiar Euclidean space. We have the sphere, and we also have some beautiful structure like special orthogonal, and even the exceptional group G2. So these are called symmetric spaces. Geometry perfectly balanced that they look the same from every point. And these are actually the playground for symmetry. So in this playground, I asked a core question. Are Killing tensor decomposable? In other words, can they be broken down into simpler one, like protein into amino acid? So what are the basic component? Well, they are the Killing vector. So they are visible symmetry that we can all picture, for example, moving back and forth, or rotating in place, or standing still. If you imagine having a round ball and you rotate it, it looks the same from every angle. That is Killing vector in action. So after a lot of mathematical work and computers calculation, I figure out the answer, and the answer is absolutely yes. On every symmetric space so over here, Killing tensor are fully decomposable, and they can be broken down into smaller Killing vector. So why this matter? Because it actually illuminates why conservation law govern our physical world. So it is a vital step in to understand our fabric of the universe. Thank you, everyone.
Thank you very much, Kian. Appreciate it. Please be seated. The following presenter will be Chao Lin Er. Chow Lin Er. Thank you. A big hand to him. Thank you.
Okay, at first I thought that the Nobel, the Laureate Forum is something to do with Nobel laureate. So I was going to talk about a recent work that has something to do with Nobel laureate 40 years ago, but turned out to be a sole laureate. But in any case, keep the slide. so in any case, so in 1986, this is the original paper published. And then they got a Nobel Prize in 1987, so it's 1 year later. I would say probably this is one of the quickest Nobel Prize being ever awarded to them. They're very lucky. So actually the work was about the discovery of high temperature superconductivity. So high temperature per se is about 30 degrees above the absolute zero. In the one class of materials is called ceramics. So it's oxide-based materials. So I think when the Nobel Prize committee, they have this idea that, okay, now we have these discoveries of high temperature superconductivity in this one example of ceramic material, copper oxide. Then it should be a lot more. Then that's why the Nobel Prize given to ceramics. But surprisingly, for the last 4 decades, copper oxide is still the only oxide that is having these properties. So it's not so good, right? So one of my motivation when I started this work on superconductivity is to address this by saying that, okay, let's think about this as a proof by induction. I want to start from the one material and have to be able to generate another material that similarly holds the same property. So in this case, we turn to another oxide, so a non-copper oxide. And yeah, it takes a bit of time, then eventually we reach there, but we can get a high temperature superconductivity, in this case, more or less about 40 Kelvin, so about 40 degrees above the absolute zero. So I guess it's the first step to kind of prove that the original Nobel Prize was, makes sense, that we, there is a lot of hope for ceramics materials to have these properties, high temperature superconductivity. So that's the thing about it. So if you have any question, you can feel free to check out the paper, and my corresponding address is also there. So okay, so again, I will just stop here. So let's make superconductors great again. Come on, guys.
Thank you, Linga, for calling to actions. That's cool. Okay, next we will have Mohammed Aviv Rahman. Mohammed, please. Thank you.
Yeah, so good evening, everyone. So my name is Afif, and I'm currently a final year PhD student at University of New South Wales, Sydney in Australia. And my main field of mathematics is number theory, like kind of mathematical branches that, put it shortly, considers like the interactions between and works between like the integers, the kind of things that go like 1, 2, 3, and etc. And even though like the objects are pretty elementary, and you might ask like some elementary questions regarding that, in fact, this kind of field gives us like some very deep and very profound questions in the whole of mathematics, like Fermat's theorem, or maybe Collette's maybe Riemann hypothesis. And in particular, my kind of number theory works in arithmetic statistics, which works with studies the statistical distribution of some mathematical objects. So for example, let's say you have some equations that comes from the matrices. Let's say there you have 2 times 2 matrices, A, B, C, D, and you already know that to count the determinant, you just do the cross product and got AD minus BC. And let's say you got some numbers in there, and you know that you can compute directly and got, let's say, the determinant is 5. That's pretty easy. And after that, my main kind of question is what happens when we reverse the questions. Let's say we want to make the matrices have determinant 5. Of course, that means like AD minus BC equals to 5. And you need to find like all A, B, C, D that satisfy the equations. That one is that one is like you have like 4 variables, 1 equation, so like infinitely many solutions. And that's infinitely many. But the questions will be a bit more the same if you like replace the 5 into like 10 or 20, you got the infinitely many solutions. But you expect there will be like some difference between like the ABCD, which gives solution 5, and ABCD, which gives the 10. So like you want to compare 2 of them, like which one has like more matrices and stuff like that. But since here we worked with with like infinitely many solutions, and that's where the arithmetic statistic goes in. So we limit some of the variables and decided based on the distribution, like which one has like the asymptotical formula and which one has like more solutions and which one has less. And there were like many other kind of questions in this kind of fields. For example, you can just compute like the rank or maybe the characteristic polynomial. And in fact, you can also work with other variables with, other mathematical objects with many variables such as like polynomials or maybe like vectors, or maybe you can make the matrices bigger, like 900 times 900. Yeah, you can do that. And maybe you would like to ask some questions like, why is this kind of thing useful? Well, this kind of thing appears in the cryptography, and I won't say much because I ran out of time. But for further information, you can just scan the link to my QR code to my homepage. And thank you, everyone, and thank you, HKLF, and I hope to see you soon.
Appreciate it, Avi. Thank you. Okay, so let's invite our next presenter, Claire Lessler. Claire, please.
Oh, pitch clock. Okay, cool. Hey, everyone. My name is Claire Lessler. I'm a PhD student at the University of Chicago. Oh, yeah, I'm short. Is what it is. I primarily work on improving maps of the cosmic microwave background by trying to better understand the systematics that go into the measurements that produce those maps. So in principle, the techniques that I'm working on to improve CMB maps are applicable to basically any microwave telescope. But for the purposes of my PhD, I'm working on the Large Aperture Telescope for the Simons Observatory, which is in the Atacama Desert in Chile, and which I've included a picture of so that you pay attention. So what's the CMB? Why should you care about it? So the CMB is this relic radiation left over from the Big Bang, and it's essentially a snapshot of the universe about 380,000 years after the Big Bang. So it's cool. So you can learn a bunch about the composition of the universe and about its history from measuring the patterns of the CMB across the sky. Among these things, you can learn what happened about 10 to the minus 33 seconds after the Big Bang. You can figure out how quickly the universe is expanding and learn things about its composition. Now, one of the tricky things about making measurements of the CMB is that in addition to measuring the background, which is a background, you also see everything else in the sky that emits microwaves. So you see a number of foregrounds, including dust emission and something called synchrotron radiation. And so traditionally, the way we separate out the background from all of these foregrounds is by using the fact that all of these things are basically different colors. A consequence of this is that any error in how you understand the frequency response of your instrument directly translates to an error in your map after you try to do this foreground separation. And so I focus specifically on understanding the bandpasses, meaning the frequency responses of our instrument to sub% uncertainty. So the previous bandpass measurements of the sort of precursor experiment to SO, ACT, have uncertainties on the level of a couple %, and I'm trying to push that to below 1%. So I apologize. I've left out a lot of the technical details because my advisor told me to. But as like a taster, some of the ways I'm working on this is I've replaced lenses which contribute a bunch of standing wave like interference effects with these off-axis aspherical mirrors. And with the Fourier transform spectrometer that I'm using, we get these positional and focus-dependent spectral shifts. And so I'm building a robot that can move in 3 dimensions and couple it to our telescope so that we can calibrate a lot of those shifts out. So how much time? I got 18 seconds. I'm broadly interested in electronics and instruments and systematics, and I like learning new things. So if you're interested in this kind of stuff, come talk to me. Thanks, guys.
Thank you very much, Claire. Looking forward to more ideas exchanging. And our next presenter will be Jeffrey. Jeffrey Chu. Jeffrey, please. Over to you.
Good afternoon, everyone. I'm Jeffrey Chu. I'm assistant professor from the School of Statistics at Renmin University of China in Beijing. So I just want to introduce a few ideas related to our work on network analysis and fraud detection in digital asset markets. So obviously, the financial sector has experienced a lot of disruption from the rapid development of blockchain technology and also digital assets, digital currencies. But obviously, these ideas are not exactly payment methods. But what we notice is that a lot of these are related to a lot of financial activities and also fraudulent activities. So our idea in this work is to say, are there any kind of novel or interesting ways we can model financial transaction data from blockchain-based systems? And so we say, yes, we can borrow some ideas from statistics, econophysics, in the form of network analysis. So what we actually consider is to take financial transaction data from the blockchain, and then consider this or model it as temporal graphs, very simply, where the nodes represent accounts, addresses, and the edges or the links between these nodes represent some kind of connection or relationship between these accounts. So our work focuses on two main areas. One is very simple statistical network analysis of how the properties of the network structures of these graphs change over time and how they link to these changes in economic variables, so how they're influenced and how they also influence each other. The second part of our work focuses also on saying, can we take these ideas of learning these structural patterns in these graphs and networks, and then apply them to cases where we have labeled data. Maybe we have normal and fraudulent transactions. And we find that, just to kind of save on the details here because of time, if we combine these ideas of the basic structural properties of these networks, but also bring in some ideas from topological analysis, where we consider higher order structural patterns in these networks. If we combine these together, what we actually find is that this actually improves our fraud detection in these financial transaction networks. And this is particularly the case when we have, as is very common with financial data, very limited labeled data in terms of, say, fraudulent data compared with normal transaction data. So that's just a very brief summary of our work. If this is interesting to you, I'm happy and open to discussions later on. So thank you very much.
Thank you very much, Jeffrey. Please be seated. And let's invite our next presenter, Chung Ka Wai Adrian. Okay, Adrian is him. Big hand to him. Thank you.
Thank you. So I'm Adrian. I'm a postdoctoral fellow at the University of Cambridge. I extract fundamental physics by analyzing gravitational waves. The physics that I'm currently focusing on is the validity of general relativity in the strong field regime, where gravity is very, very strong. And to this end, I listen to the sounds of black holes collision. When two black holes collide together, they will merge to form a new black hole. And this new black hole, right after the collision, is rather distorted. It will settle down into a stationary black hole by emitting gravitational waves that are decaying and consist of a set of characteristic frequencies, like a beating drum. And by comparing these measured frequencies in gravitational waves against the predictions by general relativity, we can test Einstein whether it's right or wrong in the strong field regime. Well, it sounds very straightforward, except that it's not, because we first need to understand the oscillatory frequencies of black holes in different setups, especially in theories alternative to Einstein's. And to this end, that will require solving a set of complicated equations. And in the last Laureate Forum, I began the development of such a formalism to compute the oscillatory frequencies of black holes. And following 2 laborious years of work, I managed to compute the oscillatory frequencies of black holes in several gravity theories as labeled by the dragons in the legend. You don't have to understand it. That just means the specific way in which Einstein's general relativity is violated. And my calculations lead to some of the first accurate computation for some gravity theories. And then using these frequencies, I analyzed the gravitational waves that have been detected by the LIGO detectors. And here is the result for tests of various gravity theories. So the bottom line is no violation from general relativity is found. I did not find any mistakes from Einstein, so I cannot join you as a Shaw or Nobel laureate. And yeah, this is pretty much the end of my work. If I can explain my work in 3 minutes to you, it shouldn't take me 2 years. So please come to me after this talk if you are interested. Thank you.
Thank you, Adrian. Looking forward to more ideas exchange afterwards. And our next presenter will be Chan Stephen Pang Fai. Thank you, Stephen. Stephen is over here. And the stage is yours.
Okay, hello, I'm Stephen Chan, Associate Professor from American University of Sharjah in Dubai. Okay, one of the projects I'm going to quickly go over is a project that I work with the Green Planet Dubai, which is one of the largest tropical rainforest zoos in Dubai with over 3,000 species. One species that I'm looking at is this beagle slow loris. It's a very endangered animal, and again, it's non-native to the Middle East, and it was found in the Middle East, and we took it in as the Green Planet, okay? As also I'd like to say it's very venomous, and if it bites you, again, it's very dangerous. So, as it's endangered, it's very important to look into how to look after it in captivity. So we spent over half a year creating, as you can see here, different enrichments that we can put in an enclosure for this beagle slow loris. Okay, some of the enrichment we created includes hanging melons on strings and leaving it there. On top of that, we put little mealworms inside puzzles and scattered it around in the enclosure so the slow loris can solve it and then get these mealworms out. We also have leaves and we put essence in, plus we have many more enrichments, and these are just some of them. But what we really wanted to look into is the behavior. So by having these enrichment, does it improve their sniffing, grooming, locomotion, scratching, and many more behaviors we looked into, okay? So we spent over 2 months studying it using ethograms, pre and after enrichment, and we looked at their behavior. What we did is we implemented different statistical analysis onto our ethogram data set. And different statistical analysis that we use include Bonferroni tests, different distribution theory, chi-squared independence tests, ANOVA tests, and we statistically found that placing certain enrichments into these enclosures really improved the behavior and the lifestyle for these endangered animals, okay, at the Green Planet. Again, this just shows you that just placing certain enrichments for non-native animals in captivity, which are endangered, can really improve the lifestyles for these animals. And it's very important that this kind of studies can be replicated in any endangered animal in captivities worldwide. Okay?
Thank you. Thank you, Stephen. Please be seated. Then we will have our next presenter, Damon Jung. Damon? Okay, Damon is here. A big hand to him.
Hello, I'm Damon Chen from University of Michigan. So I search for continuous gravitational wave signals. So unlike the gravitational signal we detect from binary merger, continuous signal, binary merger signal just lasts for 1 second, but continuous signal is long-lived persistent signals. If we detect such signal from like fast-spinning non-asymmetric neutron star, then we could use it to infer the neutron star properties or the equation of state. One unique thing is that once it is detected, even without any detector update, as long as the detector is keep operating, then we'll have a longer data set containing such signals, so our inference will have a higher and higher precision. So the physicists could use it to refine their physical model with higher and higher precision over time. So, searching for such signal using a year-long data or even 2-year-long data is pretty computational expensive. So I explored the deep learning techniques to search for such signals. So here I train a attention UNet. The UNet is mapping the noise spectrum input to a clean signal output. So I trained it using such pairs with a mean square error loss. The mean square error loss separate the signal pixels and the noise background pixels, such that the training could balance the noise suppression and also keeping the signals. So at the bottom, I'm showing the performance. So here I'm showing 2 examples. Left-hand side is a 20 Hertz simulated signal, right-hand side 500 Hertz. So notice that you could barely see the signals on the top row, which the noise amplitude is 20 times higher than the signal amplitude. But the trained model could output the noise output at the second row, which you can see is pretty similar to the ground truth at the bottom. So it doing a pretty good job. And how can we use it in the search? We could sum up the power of the spectrogram and as our detection statistics. And by fixing the false alarm rate to be 1%, then we plot the sensitivity or detectability on the right-hand side. That's the blue curve. And comparing to the black curve, which is a benchmark, using a benchmark match filtering method, you can see the machine learning is not as good as the benchmark model, but following the same train, meaning the model is not undertrained or overtrained. But it's by far it has a comparable sensitivity to the best deep learning-based approach in the field. But I think we could do a better job, and hopefully it could help us for the first detection of continuous gravitational wave. Thank you.
Appreciate it, Damon. Thank you. Let's invite our next presenter, Kevin Lamanta. Kevin, please. It's yours 3 minutes.
All right, last one. I'm Kevin Lamanta from UNSW, University of New South Wales, Sydney. So I'm just going to briefly mention what I did in my PhD. Central to the idea of Fourier analysis is this notion of integration of functions over the very basic, say, the unit circle. So what I'm doing here is just change that framework so that now we're working in finite fields. So this is this sort of number system where you can say things like 2 plus 3 equals 0. So that, well, this allows us to talk about this Fourier analysis over finite field, this new number system. And we're not just considering one geometry, the Euclidean geometry, but also the hyperbolic geometry. So just to show you what it's like to integrate over sphere in general, over the real number R, we do have this sort of formula explained in this gamma function, where this occurrence of pi is hidden. And this formula is very much in favor of even numbers. So if the powers are all even, you do have this formula involving this gamma function, but if one of the exponents odd, then it's 0. Right? So specifically, if you have n equals 2, which gives you this unit circle, you do have this sort of nice number. And if I normalize them so that I have integral of 1 equals 1, this is a family of rational numbers. But if you just look at the things involving this sort of factorial notions, it's actually a family of integers called super Catalan numbers. So it's a very interesting object in combinatorics. So now, if we extend this to finite fields, I just insist that, well, we have this sort of integration which obeys three things. Basically, I insist that the integral of 1 equals 1. Then, if you have a function that allows you that restricts to 0 on the circle, you do have 0 as your integral, and it is invariant under rotation. And in this case, I'm just going to mention that it's restricted to polynomials only. And basically, the formula, this sort of integration, you can actually prove that the only integral that makes sense under these three conditions is this sort of summation formula, or averaging formula if you like. And moreover, we can actually say something more about this. So the integral can be explained as basically this scary-looking formula over there is just this polynomial pi mn, I call it, in variable alpha, and you just basically take selections of the coefficients in that variable alpha. And for example, if you have this condition, it actually extends nicely to the real number case. All right, so that's all. Thank you very much. Thank you.
Thank you very much, Kevin. Thank you. So here comes our last presentation. Let's welcome our last presenter, Herschel Wang. Okay, Herschel, your time for 3 minutes.
Hello, everyone. It's my pleasure to be here to share my research. Good afternoon, ladies and gentlemen, professors and young researchers. My name is Herschel Wang from PolyU and NTU. I was graduated from PolyU and become a postdoc in PolyU for 2 years, and now I'm a researcher at NTU. So have you ever encountered such a problem? When you want to charge your smartphones, you find what? A cable, right? However, we tend to find this. All the coils, wires are tangled with each other. Really annoying, right? So how to figure out this problem? And that should be related, perhaps, my research, wireless power transfer. And my research philosophy inspired by William Shakespeare, to couple or not to couple, that is a problem. Because nowadays, when we want to charge our smartphones, we have to put the transmitter and receiver closely without any misalignment between them. So these are the two things that we want to improve. One thing is that we want to improve the air gap between the charger and the receiver. The other is that we want to make a free room, like we can enjoy our power, like what? Like our Wi-Fi. So to couple, we have our Helmholtz coils. We use our Helmholtz resonator to create a uniform to charge our e-bags. And we also have our EV systems. We have our dynamic chargers in the road and can charge our trams or trains, so that we have a great collaboration with our Hong Kong MTR and Singapore MRT. Okay, in the end, I would like to end up with a quote from Steve Jobs. Simple can be harder than complex. And that is just like our research, exploring new technologies. Mathematics, astronomy may be math very difficult, but we can bring a simple and bright tomorrow. Thank you very much.
Thank you very much, Herschel, for being our last presenter for today. And thank you so much, all young scientists. So we're so excited to have listened to nearly 30 very innovative and inspiring ideas from all of you. I believe that you might have found some interest in different presented subjects, or in some ways, you were actually inspired with new ideas today. A heartfelt thank you to all the presenters for their contributions. Let's put our hands together to appreciate them, and indeed, actually yourself. With your passion and dedication, I believe that there will be more and more groundbreaking researches in the future. So here comes to the end of the flash presentation. Thank you very much for joining us. For our honorable laureates and foreign participants who have enrolled for the dinner, we have arranged coaches to transport everyone to the peak. Please arrive at the coach boarding area at Building 15W. Building 15W is actually, you need to get across the Building 12W before 5:45. Before 5:45. Should you need any assistance or clarification of the venue to board the coach, please approach our event staff outside the hall. Thank you very much, and have a wonderful evening and the days upcoming in the forum. Thank you.